right, so I'm supposed to start. I guess some people will join later, but I guess we'll try to stick to the schedule. So my name is Stephanie Balzer. I'm also from CMU. I do research in programming language theory and more particularly right now, session type concurrent programming. And exploring the connections to linear logic. So this is what I want to talk to you about today. As you know on the schedule, basically I called the session session type concurrent programming. So let me write down. So because of my height, I won't reach the top part, okay? Which means that I have to clean more regularly, but I guess we're going to be fine. All right, so I can actually, at least I can pull it up and down, so that's already good. And you already noticed, so let me write that down. Okay, so that's basically what I'm going to talk about. And I assume most of you have attended last week where we talked about parallel programming. So here, notice that this is going to be about concurrent programming. And in the development, we will understand what the difference is, okay? But just very briefly, in parallel programming, you want to be able to reason sequentially about your code, and it's all deterministic. And Guy and Umut also showed to you how to derive a cost model for your language, so that you actually know how fast things are going to be running. And in this setting, especially in the later part of the lectures, we will see that we deal with non-determinism. So that's something fundamentally different. There is some recent work in linear session types that tries to reason about program and determine some abstract notion of cost. I'm not going to cover this in this lecture, but still there is no cost model in the sense that Umut and Guy have developed it. All right? So let me give you a brief roadmap of what I'm going to cover. So let's write that down. Oops. So because I'm kind of a top-down, bottom-up person, so that's how I'm going to do the lecture. I want you to know basically where we are going, and then we go by iterative deepening. So I will talk about one model of concurrent programming, which is message passing concurrent programming, okay? And then, in terms of how to type those programs, we look into session types. So we use session types, right? Yeah. Oh, it's bigger? Okay, good. So in order to, so I'm not going to rewrite that, right? Henceforth, I'm going to write bigger.
The first word at the very top left says
session typed. Session typed, okay? So yeah, so we are going to use session types in order to type our programs that employ message passing concurrency. And then, in particular, we are going to use linear session types. So we are going to discuss the, okay, I have to write bigger. Okay, so we are going to discuss the connections between linear logic and session types. And lastly, we are going to talk about how we can introduce sharing for session types. So in a sense, we are going to take away some of the restrictions that linearity imposes on us. We call that manifest sharing. That will become later clear what the term manifest is all about. Okay, so In terms of what are my learning objectives for this class, and I know that people have very different backgrounds here. So basically what I'm going to rely upon is what you've been shown in the first week, for those of you who have attended the first week. Paul has introduced linear logic already, using the sequence calculus, classical linear logic, and then he has shown how to use linear logic in the lambda calculus. So he derived a linear lambda calculus that used intuitionistic formulation but with natural deduction. So I'm basically relying that you have already come across the linear connectives. But what we are going to do is we are going to kind of add life to that. Because I imagine, at least for those of you who have basically come across linear logic the first time, right? It's kind of very abstract. So my goal here is to make this less abstract and to basically make sure that every one of you now understands how can we use linear logic in a programming language. Okay, so learning objectives, I'm going to write that down. Okay, so what did I write? So yeah, I want you to understand how can we program using message passing concurrency. All right, so that's one, so the message passing. Because I assume quite many of you actually just came across the term. I also want you to understand what session types are about. Because actually when you go to conferences, maybe in the future, there's quite some interest in session types right now. So you will come across session types. And then you can boast to your colleagues because you already know, right? So then, as I said earlier, I really want to basically instantiate linear logic in terms of this language. So I want you to understand what the benefits are of linear logic to programming. So there's more to it than writing inference rules. And then lastly, so we will see all the benefits about linear logic for programming, but we will also see that it adds some restrictions, like any kind of type system does. And we will see that some of those restrictions might be too limiting, especially to accommodate all kinds of programs that we might want to write. So another thing is that we are trying to derive a logically motivated version of sharing in our language. So it's about how to accommodate sharing in a logically motivated way. All right. So that's basically the outline for this lecture, this series of 3 lectures, and that's what I want to talk about. Any questions so far? The second line, I'm sorry. All right, the second line is what session types are about. Okay. All right, so I'm going to start by appealing to your intuition. Because personally, I feel like if we have the right intuition, it's ways easier to understand all the formalism that comes later, right? So let's try and do this. I have message passing concurrency here on the board, right? So how can we think about message passing concurrency? So let's start. All right. So the principal idea of message passing concurrency is basically to think about computation as happening between a bunch of processes that exchange messages with each other. All right? So we have processes that compute by exchanging messages. And the message exchange goes along channels. So the processes are connected by channels, and they use those channels in order to exchange messages. Actually, when you read Robert Harper's book, you can see that he even abstracts away from that. And he says, you can think of channels as symbols. That's just a side note. But the classical presentation is to think about processes that exchange messages along channels. So I'm just highlighting the keywords. All right, so let's draw some processes here. So we have a network of processes. Okay, and then I have here 5 processes. So I represent the processes by those bubbles. So I have processes P1 to P5. And they're now connected by channels. So for example, here process P2 and P3, they're connected by channel that I call B. Then we have those 2 guys are connected by a channel C. Then those 2 guys are connected by a channel D. I mean, I'm just making it up, right? I'm just showing you, give you an example. And then, and that's kind of the interesting part, which I really want you to pay attention to. So far, I have basically always two processes that are connected by a channel. But in its full-blown version, it doesn't mean that only 2 processes always connect along a channel. But instead, we can also have something like this, where actually there are several processes that share a channel, and that's my channel I refer to as A. Okay? So we have channels A through D. Okay, so the important part here is that, let me use some colors maybe, that we have so-called n-ary channels. So in particular here, that's the case for channel A, right? Because it's shared among processes P1, P3, and P4. Okay? So what does that now mean? Let's think about this for a moment. So let's assume that process P1 sends a message along channel A. Who's going to receive that message? Sorry? Right, either of P1, P4 and P3 can receive the message. So what does that mean now for our programming model? If we don't know up front which one of the 2 processes is going to receive the message, yeah?
When we would send message, we will make this field aware we want to send the message, right? Or we will just randomly send message and it can go to any process?
I didn't hear the first part. Can you repeat?
Process 1 wants to send message to process 2.
Yeah.
So when we're sending message, we will make sure that only process 2 will get that message. Right?
Okay, so good question. So your question was basically, I rephrase it slightly and otherwise tell me if I misunderstood you. But I think the question is, how can we make sure in this setting that actually the message, if we want to send a message to a particular process, how can we do that, right? Because, as we've seen here, if a channel connects several processes, either of the other two can get it. All right, we'd use a private channel. If we want to make sure that our message will be received by the process that we're talking to, we better have a private connection. Which means, for example, that's the case here, right? If P4 sends something along D, we know that P5 will receive it. Yeah?
Just to make sure you say either. I'm implying this is not like I thought first, it's not the semantic of multicast where everybody gets the message.
No, it's not. Yeah, you can implement a multicast basically by receiving a message and send it again, exactly. But the basic model is you send a message along the channel and it gets received by someone on the other end, all right? So, let me get back to my question that I asked. What kind of programming model do we get now that we have n-ary channels and this semantics? Yeah?
We have non-determinism.
Exactly, we do have non-determinism. And now I link back to what I started out initially, right? Fundamentally, this is a different programming model. That's no longer parallel. That's now concurrent because we don't know how things are going to happen. Non-determinism. I always have to be, when I write and talk on the board, it's very difficult not to misspell. All right, so we have seen, so here the example would be when if P1 sends along A, either P4 or P3 can receive, right? Okay, so this kind of programming model has formal underpinnings. Like functional programming is based on the lambda calculus. Here the formal model would be process calculi. Okay, and in particular there's one which is famous, like depending on who you talk to, some people say it's equally important to the lambda calculus, others might disagree. But anyway, if you look in the literature, you come across this. So basically the formal underpinning is our process calculi in particular the pi calculus. All right, and the pi calculus, that was, I write that down, you certainly have already heard the name. So that was developed by Robin Milner. And so there's a ton of literature on the pi calculus, but basically this is one of the first papers. And for those of you who are interested, I can point that out. Yeah? Oh yes, right. I'm sorry about that. Okay. I wanted to use the keywords basically in green, but the green is apparently difficult to read. Is that right? Okay, so I'm not doing it. All right. Another thing I want to point out with the pi calculus is that actually it has been shown to be universal, which means that Robin Milner has shown how to encode the lambda calculus in the pi calculus. So in a sense, that shows that they're equally expressive. Oh, I thought I would put down the green one, but apparently not. Okay. So the pi calculus is universal. All right. Okay, so the next thing I would like to do is to make this a little bit more concrete by going through an example. Any questions up to now? Yeah?
Just a clarification on either P3 or P4, does that include both, or is that like exclusive?
It's exclusive, yeah. It's an important question because that gives rise to non-determinism, right? Because we don't know who receives the message. It's either or, so exclusive. All right. Okay, so I guess I can use this board over here. So I want to play around with this, still using pictures for now, and implement a queue with you in a message passing style. So come up with a bunch of processes that simulate the interaction between a client and a queue. Make sense? You're all computer scientists, so I don't have to explain a queue. So that's good. All right. So let's do a message passing queue. Okay. All right, here we go. Okay. So certainly we're going to have a client process, right? So let's write that guy down. So here we have a client. And then there has to be basically a queue, right? So for sure, we have a queue process. And they interact along channel Q. All right. So for the purpose of this example, let's assume that in this queue, we store characters. Okay, so where do they go? I'll just write it down for now. So essentially, or let's explore that. So essentially we're going to put, or what I'm going to do is basically for each character I'm going to have its own process. So a process, each process basically contains one character. So let me write that down. All right. So this guy stores O, this one stores P, this one stores L, and you can think maybe what kind of word I'm going to store in that queue. All right, so what you can see is a way to represent the queue, the one I've chosen right now. I'm not saying that's the only one, but the reasonable one to do it using message passing concurrency with processes is basically to represent it as a linked structure, right? A structure of processes, a linked structure of processes. So we have here the head of the queue. That's the interface to the client. So the client interacts with the queue along the channel queue, and then internally we have other channels that basically link the processes with each other. So let's call them N1, and 2, and 3. And also how I'm going to build the queue. Yeah, so 2 questions.
Is the label on the head?
On the head that says client. You mean here? Oh no, I'm sorry, head. Q, that's Q.
Head of Q, so up on the top left, that's a Q?
That's yeah, okay. Lowercase q, lowercase n1, and 2, and 3. Yeah, and there was another question.
Computation over it, right? So processes basically compute something over the data.
Yes.
So why we have this notion of storing something in processes?
Okay, so the question is why would we even bother about basically have local state in processes? Because the basic computational model is by exchanging messages, right? That's the question. So as you can imagine, it's really helpful to have some local state. Just imagine to compute the factorial, for example. It's like when you do in a functional programming language, you also have local state. Okay, I shouldn't call it state, right? But you get the idea. or by recursion, we can basically maintain some state. And the same holds true here. In order to do practical programming, it's helpful to have the possibility to associate some local state with the process. Can you accept that for now? Okay, so don't think about it too much, okay? Later on when we'll make examples, we'll program probably tomorrow. You will see that we really need that, okay? All right, so what I'm also going to do is, how I'm going to program with that queue is that it's a queue, right? We have to maintain the property of first in, first out. So what I'm going to do is essentially that I will dequeue from here and I will enqueue at the end. Also note that here I have basically a process that doesn't contain any character. This is I chose a sentinel representation of the queue. It's easier to program that way. Most likely tomorrow we're actually going to implement that in code. Then you will see how we do that. But I assume that you're all basically familiar with the sentinel representation of a data structure, right? Okay. Okay, so now let's play with that queue and let's enqueue the next thing, which is going to be OPL. Okay. All right, so let's enqueue. All right, just okay. Question?
The word there, the last bubble, there is a...
It's enqueue.
Okay.
Yeah. So this one is a DQ, so DEQ, NQ, ENQ. All right. All right, so now let's think about once we are going to enqueue this, the next letter here, how is this list of processes going to change? What kind of picture I am going to draw?
Same one, but with an S at the end.
The same one, but with an S at the end. So, and with one process more, right? Okay. So we are going to get this. I try to align them under each other. Oh, my circles are no longer the same size. I'm sorry about that. Okay, so still we have the client here. We have the Q here. We have the O. We have the P. We have the L. Now we have, I'm trying not to turn my back to you, but I know that it's difficult to write. All right. So, and then, so basically, we get this. So we observe that we have one new process. So by enqueuing, we created also a new process, or in our lingo, we spawned a new process. Okay. All right. So we're not going to really put in the OPLSS into this queue, but we are going to dequeue right away. So let's now, as the client, and maybe I should point out when we enqueue, what it means is basically that the client sends the enqueue message to the head of the queue, and now the client is going to send the dequeue message to the head of the queue. So there was a question somewhere. Yeah?
That was my question. You just said that client sends so client is not connected to the last process.
Correct. Correct. Correct.
That message is...
Yes, correct. So the question is basically how things are connected. It's indeed the case that the client only interacts with the head of the queue because the client is only has a channel queue, shares the channel queue with the head of the queue. So when the client sends the enqueue message, what happens, and now that's an interesting question. What happens, or what must happen internally, is that somehow the queue, when it receives the S, internally passes the S down, right, in the queue. So meaning that this guy now says to this to enqueue an S. And this guy says to this one, I want to NQNS, and then once this guy receives it, it says, oh, well, okay, I have space. So I create a new sentinel, and I'll become the S. Okay, we're good? So what happens now when the client sends the DQ message to the head of the queue? Yeah?
So it receives DQ and removes itself, or like end of this.
Right. It's basically the head of the queue is going to remove the DQ, and it says, okay, that's what I contain, it's the O, and I'll cease to exist. Right? So we basically get this. Okay, so here we have the P, then we have the L, and the S. And then here we basically have N2, and 3, and 4. All right. So that's how we can just pictorially implement a queue in the PyCalculus. And believe me, now you've already basically understood how to do this. Everything else that is coming is basically learning a syntax and more concrete knowledge. But now I set you up. You have the right, hopefully the right mindset. Okay, so, yeah, question?
Is NQ and DQ messages sent by client to the queue node? Correct.
Yes. Right. So the computation happens by exchanging messages. So the question was, NQ and DQ, are those messages sent by the client to the head of the queue? Yes, these are messages. Okay, another question there. How does the client establish a new channel with what, just in general? Okay, so let's get back to this again. So the question was, how can the client establish a new channel with the end of the queue? Well, the client doesn't do that. It just happens as a result. So let's review that again. So the client, so you're basically talking about the NQ case, right? So the client sends the message NQ to the front of the queue. And as we can see, as a result, internally the queue changes by creating a new process and having a new channel to that process, right? So it spawns a new process here. But that happens internally to the abstraction. So you can think of this as an abstract data type, basically. So what the queue does internally as a client, you don't know. This is information that is not that's not public to you. So, but internally, how that happens is basically, as we are going to implement it, is that the queue then sends the NQ message to the next guy in the line, and this guy sends the NQ message to this one, and once we get to the sentinel to the end, then this guy is willing to store the element that it receives. Yeah? So which process P? So the client does not have a direct channel to the tail of the queue.
No, it was to the head in the DQ where the O ceases to exist.
Oh, so, I'm sorry. Yeah, okay, this P you mean.
Yeah.
Oh, okay. Okay, sorry. Thanks. I now understand the question. Yeah. All right. That's a good question. So how does this come about? Because previously the client was connected to this process, and now this process ceases to exist. How do we make sure that now this kind is just not, it's basically a null pointer, right? We don't want that. So once we go look into the connectives that we're using in terms of programming, this will the way how this happens or how we achieve this is we use something called forwarding, which is essentially identity in logic. All right? But we'll get to that. So for now, you can think of it operationally by basically saying, in an implementation, we could say, well, okay, every process that happened to talk along Q will now just, so essentially what we do here is we create a new channel Q prime and then internally equate Q with Q prime. Or basically what we do is everywhere where we have an occurrence of Q, we replace it by Q prime. Okay? That's one way to do it. Another way would be to basically, in an implementation, okay, to keep this process alive and just have it forward all the messages that it receives. That's another possibility in terms of an implementation. All right, but good question. Sorry, when I prepared, I didn't realize that that's something that I have to explain. So I'm grateful for your question. Okay. All right, so now let's detail something more. Another concept I want you to understand based on this figure. So here, what we've done is basically our messages were so far sending of what we call labels, so the NQ and the DQ, and also then the sending of actual values, the things that we want to NQ, right? So the S, for example. But as it was originally conceived, I guess, in the pi calculus, there was no support of basic values like integers or strings or characters and so forth. But the idea was essentially to so the messages, the only messages that you can send are channels themselves, or more concretely actually, or more precisely, references to channels. Okay, and now you might feel overwhelmed and think like, what the heck does that mean, right? Sending a channel along another channel? All right, sounds confusing at first, but you all know kind of programming with references, right? Be it object-oriented or whatever. So it's the same idea, right? We don't send an actual object or an actual value, but we send a pointer to the thing. Same idea here, right? We can send a channel reference along another channel, which then means that the recipient will now have access to that channel also and can talk to the process that is behind that channel. All right, so what I want to draw another picture here because that's important. So that means, so if we now have this queue, and rather than storing in the queue basic values like a character here, and that again would be our client, okay, and that would be the head of the queue. So pictorially, how can we think about this if we are going to now store in the queue channel references? Well, it means essentially that this queue now, this element here, is now connected, right, to another process. So it basically stores in here a channel, let's call it C1, right, and then here C2. Okay. So basically we don't only store a value, a basic value, but now we have a channel reference, which means it gives us the possibility to talk to another process along that channel. All right, everyone good with that? Yeah?
That process is already there, right? We're just sending the channels, not the...
Correct, the process is already existing, which is, exactly. So what does that also mean? It means in particular that because that process, that channel already exists, it means that actually we're not the only one talking to that process, right? There might be another process, P1, that also shares that channel C1 with me. Okay? Yeah?
When I pass someone a channel, have I given them access to read from it or just put things into it?
Okay, so question was, if I pass a channel, what are the kind of obligations or capabilities I pass with that? So does it mean I give only read access to the channel or read and write access? Very good question, because it already kind of foreshadows what we are concerned with basically in terms of reasoning about the program, right? So in the PyCalculus, if we pass a channel, you can send and receive messages along that channel. There's no restriction so far. And that's why we then talk about linearity, right? To reason about the programs. Yeah?
If a node has two channels, is it able to discriminate? Is it able to do different things depending on where the message comes from? Or if the same channel will always be treated the same way internally?
The question is, if I understood that correctly, is can you basically discriminate where you get a message from, right? So in this model, just using the bare constructs, you can, but you can of course do it somewhat operationally, right? You can set up a protocol that, for example, whenever you exchange a message, each process sends first its identity, for example, or something like this. But that's something you would have to set up operationally. So this is just a calculus. We don't even have types so far, right? We just exchange messages. And in the bare calculus, it's just we exchange channels. That's it. Okay. All right. So yeah, so we have noticed once we send channels along channels, we can actually connect more processes with the same channel, right? Alternatively, another possibility is if, let's say, let's do the following. Okay. So we have here, oh no, I'm being consistent, so I call the processes P. Let's put them inside. So I call this P1, P2, and P3. And now here I have channel A and channel B. So let's assume now P1 sends P3, sends along B the channel A, right? So I'm just pointing it out because to make somehow the terminology clear. So we have P1 and we have P3, so that's B, and we basically send along B, we send the channel A, okay? That's what we are going to do to get from this picture to this one. As a result now, we certainly have P3 now connected to P2, right? Using A. So if P1, basically in its continuation, after it has sent B, the channel A along B, if it still keeps a reference to A, then we have this picture, right? But it might not, right? Depending on whatever we program. Then actually the resulting picture can be the one I drew initially. So I'm going to have this dotted. So the reason why I bring it up is because this thing, so the idea that we can send channels along channels, that's, maybe I can open this guy, no? That's referred to as mobility in the PyCalculus. And I'm just writing it down because you might come across that terminology. And I think really to call it mobility really only makes sense when we have the picture where P1 no longer has a reference afterwards, right? Because then literally this connection is mobile, right? It all of a sudden is now connects different nodes in the network. But it can still be the case that P1 maintains a reference, in which case we have like an n-ary channel. All right, so in a session type setting, we basically refer to the same thing as higher order channels. So when you go to the session type literature, that's what is referred to as higher order channels, which means basically the idea that channels are higher order because they can also transport channels. Okay. Good. So that's basically where I want you to be. And let's move on. I'll take a sip of water. And then I'll have to... I still can keep everything on the board, I think, for the next thing. So far we have just basically, we have the process calculus, which is just computing by exchanging messages. But we're here at the Oregon Programming Language Summer School, right? And all along you've heard about types and the benefit of types. So I believe in types. I love types. Not everyone does, but I have my bias, as everyone else. But I think there are good arguments for types. But anyway, so because I'm giving this lecture, we are going to talk about types now. So how can we describe the protocols that arise from passing messages? How can we type message passing protocols? Well, the answer is on the board. What do you think? Session types, yes. Because we can think of a protocol that describes how processes interact by exchanging messages as a session. Okay, so let's talk about session types and see how that helps in typing the queue protocol that we just looked at. Okay. All right. So now we talk about the types for protocols of message exchange. All right, and as I've just said, we use session types for this. And session types got introduced by Kohei Honda, okay? In 1993, that's the seminal paper. Unfortunately, Honda already passed away at a young age. But he has been very influential, and everything basically relying on session types goes back, is based on his initial work. So let me just introduce the session types right away. So I'm going to use some, so of course when you go to the literature you find different syntax. And I basically use the one that you in papers, but just be aware there are differences between the syntax used in papers as everywhere else. So let me write down the abstract syntax of the types. And I'm going to use the letters usually in henceforth for basically session types. I'm going to use the letters A, B, C, and D. Okay. So right now I'm just using A. And but before writing it down, I think we can derive it together. So what constructs did we use so far when we were playing with the queue? So if we were to design session types, what type constructs, what connectives do you think do we need?
Well, we need processes.
Yes, we do need processes. Now, I want to think about the types though. Okay, oh, you were over there. I was kind of glaring, trying to identify. Yeah, so messages, so like the NQ and DQ, right? So we have to have a way of basically communicating whether we want to NQ or DQ, right? Which essentially means kind of we make a choice as a client, right? We say to the process, hey, I'm going to NQ, or hey, I'm going to DQ, okay? Oh, you wanted to say that? What kind of other messages did we want to send to the queue? Channels, exactly. So, right, and I already said send, right? So we want to be able to send a value and receive, exactly. Okay, so we need somehow, we have to have the possibility to send something, to receive something, and also to indicate a choice, whether we want to do A or B. Okay, so now we have it already. All right, so I'm using this syntax. Okay. All right, this means that the question mark, what does it mean? It's to receive something, right? It's an input to receive something. So if a process has this type, so question mark brackets T dot A prime, so how do we parse this? It means I am willing to receive an input of type T, and after that, I continue to be a type A prime. Okay? So what's the inverse? Well, it's to send, right? And here we use bang for it. So I am willing to send a value of type T, and after that I continue as an A prime. So I used here T, so let's write that down here. What is T? Well, T can be a session type itself. In this case, then we can send a channel along a channel, right? But also it can be a basic value. So it can be an int, a char, and so forth. Okay? I'm not going to bother about writing it all down. That depends on your particular session type formalization. Okay, so, all right, but then we said, well, we also want to be able to indicate a choice, right? We wanted to say to the queue, well, we're going to NQ something or we're going to DQ something. So, in the session type literature, usually, we use a connective from linear logic to express a so-called external choice, which means a choice that is given to the client. So it's external to the process, so the client chooses. And so we have expressed it like this. So the way how to parse this is, if a process is of this type, it means that it gives the choice to the client to pick any of the labels L1 to Ln. In our case, we had two labels, they were NQ and DQ. And after that, it continues as type A1 or A1 to AN, depending on which label the client picked. Okay? All right, so what do you think? We didn't encounter it in our example. Yeah, there was a question.
What letter or symbol is that at the front of the...
It's an ampersand. Mm-hmm. You're welcome. All right. So, yeah, question there.
We should also have the dual of the choice.
Yes, thank you. I was just about to ask that. Right, so the observation was made that we should probably better have the dual of the %, right? Which would be, for those of you who have attended the first week, would be plus. Oops, ln. Okay, so what does the dual of an external choice mean? What's the dual? Yeah?
I guess we kind of offer these things as the Q interface. We kind of offer, I have these methods you can call.
Right. So the dual means it's internal choice, right? So the %, so the width gives the choice to the client. So the client can pick any of I offer, and I have to be able to satisfy them. So Paul made this, the example, right, with the menu in the first week, where he used % for it. Okay, and the dual now is plus, which means the choice is given to the provider, to the process, which means the client has to be prepared to deal with either of whatever the provider chooses. What was your example, Paul? Was it dessert or I forgot?
The soup of the day.
The soup of the day and right, exactly. So, okay, that connects back to week 1. So we have the same thing here. But really, I personally, for me, it's very intuitive to think of this by external choice. So from the point of view of the process that provides the type, this is the choice is made by the client, so external to the process, and this is internal choice. This is by the process itself. Okay. All right. So is there something else that we need? For example, when we look at the DQ, when you look at the number of processes, yeah?
We need to be able to kind of spawn these.
Right, we need to be able to spawn a new process. I'm not going to write it down right here because it's not a connective, it's a judgmental rule. But we also need something else, kind of the counterpart of spawning. Huh? Kill, right. We want to terminate a process. And that's going to be, I'm going to denote this by end. All right, in addition, we are also going to have basically, if you want to add polymorphism, we have to have type arguments, right? And we also want to be able to define recursive processes. So we have have to have some means of writing a recursive process. All right. So these are the session types. So now, let us write down, so given that we have this, and let me move this up because I want the space.
What was X?
It's a type argument, you know, for polymorphism, for example, right? But I'm not going to, it's orthogonal. I just want to show you that we can have basically a full-blown language. Okay, so we have this and, right, and int, and so forth. All right, so now that we have those session types, how would we write down the session types for our queue using those connectives? And a queue is a recursive type, right? And I'm going to use a equirecursive formulation of it to make it simple. So which means I can use the type itself to do recursion, okay? So now you tell me, what's the type of the queue?
It's external choice.
external choice, yeah. What are the two labels? NQ and DQ, right? First, exactly. Okay, so let's write first the NQ. Okay, after we have received the NQ label, what's our type going to be? Receive, exactly, receive the char. And after that, what are we going to be? Once we receive the char, what are the next things we are willing to do or send or receive?
Forward to the next channel. Forward that same file to the next element on the channel.
That's implementation specific. Okay, that's how we would implement it. But in terms of the type, we're going to be the queue again, right? We recurse. Okay, so, and then of course there's also the option of a DQ. Okay, now this is interesting. We didn't really come across here because when we DQ'd, actually the queue was not empty. But what if we DQ from an empty queue? Wow, okay, so now you're thinking in terms of like, like you were to implement it in C or so. But here we have a civilized language. So we have internal choice, which means that the queue can tell us whether it's empty or not. No, we don't have to deal with null pointers. Right? So, how about this? The queue tells us whether it's empty or not. So when I tell the queue I want to DQ, the queue tells me, hey, I'm sorry, I'm empty. Or it says, yeah, I'm not empty, go ahead, I'll send you the element. Right? So let's say if it's empty, I call it none. And then, assuming that we're the only client, I'm sorry, actually, I'm using a different notation here. Okay. In case we're empty, we're just going to cease to exist, right? We terminate. Or otherwise, we say, well, yeah, of course. Be my guest. I'm going to send you the char. And then I recurse as a queue. Okay, that's our queue session type. Okay, so now what I want to do next is, let's see, can I move this? Yeah, I can move this up. Oh, okay, I'm going to move this up and I'm going to erase this. We're all good with that because I want to point something out. I want to basically go back to the queue and play with it and see what happens to the type. Because that's something you're not familiar with if you haven't done this before. All right, so let's look at our queue again. So here we have the client process. What did I do? Oh. Okay, so here we have the client. And here we have the queue. OPL. All right. So now, can I use a color at all? Was blue okay? Blue is okay. Okay, I heard it in back. Oops. So, oh God. All right. So here, this channel now, we call it Q, and we type it with our Q protocol, okay? So this channel Q has type Q as we defined it up there. Okay. So now let's see. we start out with this queue, and when we start interacting with the queue, in the beginning, well, let me write it here, Q is of type Q, which means, if we unfold the type, it means it's an external choice that accepts an NQ, blah, 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 or a DQ, right? I'm leaving out the details. You can look it up there. That's how we start out with, yeah?
Is the type of the channel or the type of the process?
Good question. The question was, is it the type of the channel or the process? Answer is, it's both. Because I use an intuitionistic formulation later on, okay? But for your mental model right now, you can assume that the channel and the process that sits behind the channel has the same type, okay? All right, so now let's assume that we are actually sending the label NQ. So we do this. So now I want to know from you, what's the type of the channel now? Well, you must think like, that's a stupid question, right? Because you're not used to this. I mean, types don't change. Types of things we interact with don't change. Well, that's still true in this setting. Yeah.
No, now it's changed, so now we're waiting for the character.
Right.
We'll have Q afterwards.
Right? It has changed. Because why? Because session types tell us what the protocols are. And protocols are dynamic. They change along with the messages that we exchange. So as a consequence, the types of things change while we compute. Okay, so that's really an important takeaway here. Everyone got that? Yay, yes, okay. So other people also refer to this as stateful. Yeah, I just heard it. Okay, so now actually Q is of this type, question mark char Q. So which means if we are now going to basically send the char S along Q, we're good as a client, right? Because we do exactly what the queue expects us to do, right? So what that means is the expectation of the client, what the type of the queue is, matches actually what the queue itself thinks what a type is. And that's why the two can communicate peacefully with each other. Okay, well, so after this, what's the type of the channel Q? It's back Q, right? Okay, and so forth. So really, really important takeaway here is, I'm going to use blue if I can open this pen. Okay, so the type of a channel or a process that sits behind that channel changes with message exchange. Okay, so I want to get to, right, now that's good, we're good in terms of time. So now we've observed this, right, that type change, the type of things, of processes, channels that we interact with, they change along with the message exchange. So you've all know some type theory, right? And you heard Paul talk about type safety. Do you have any alarm bells going off? Right, there's progress and preservation. What do you think in a setting like this, what could be a challenge? If types change. Preservation could be a problem, right? So let's look at this. So look at this scenario, because over here kind of, well, there was just a client that interacted with the queue, and if the client sends a message, it knows what it sent, and the client knows the protocol, so the client and the queue will kind of happily agree on with each other. But what if we have this scenario? We have this scenario where we basically have our queue, and now we have client 1 and client 2. So let's assume that we start out with, so that's channel Q again. So when we start out with Q being of type Q. So now let's assume that client 1 goes and sends a message. And client 1 sends NQ along Q. What's the state of the Q channel afterwards? What's the type? Right. Okay. So, well, how on earth should client 2 know about this, right? Client 2 knows that it has a channel of type Q still, or that's what it believes at least, right? So client 2 now wants to send the DQ message, let's say, to the queue. So you see, preservation, if we are not careful, preservation is compromised here. Because both clients have a channel, are connected via channel to the queue process. And when they start out, they know that this channel is of type Q. If now one client goes ahead and sends a message and interacts with the queue, the other client doesn't know about this. So the other client will still assume that the queue has type, so the channel Q has type Q. So from that client's point of view, it's valid to send a label DQ. But the queue itself has already transitioned because it has already interacted with another client. So let's now write down essentially what does preservation mean in a session type setting. Well, preservation in session types means that the view or the expectations of a client in terms of the type of the channel align with the expectation of the provider, that is, of the process that is behind that channel. It makes sure that the two match up. That's preservation. By the way, also preservation is called session fidelity in a session type setting. So that's session fidelity. Okay, so it guarantees that expectation, what did I write, of client of client matches with the one of provider if they do match initially. So if we start out in a system where client and provider agree on the type, and we take a computation step, then after this step, both still agree on the type. That's preservation. So it's actually a perfect, I'm doing perfectly in time. So I started at 10:45, so I'll go until 5 past if you allow me to do that. And I can just basically end in a almost suspenseful state, which is really great for the next lecture. But anyway, so do we all agree that in the system we have right now, if we leave it as it is currently, we are not type safe, right? We fail preservation. Okay, that's not good. We're at OPLSS, we're not in industry, so we want to make sure that the languages we develop are type safe. Okay, so can we do something about this? You might take a peek at the roadmap or the learning objectives. You might also think about or remember what Paul talked about in the first week, if you attended the first week. Resource. Yeah, so what exactly did you say?
So resource can only be used once.
Okay, so the idea is, what about linearity, right? What if we use the idea of using or treating something as a resource? Because linearity makes us, maintains a precise account of our resources. It makes sure that we don't drop anything on the floor and that we consume everything, basically, right? So, all right, so that sounds really interesting. I agree with you. So then the next question would be, what are our resources? A channel is a resource. Okay, so that's the idea. We treat channels as resources. What we're going to do is that we base our session types on linear logic. Right? We use logic and all the guarantees we get from it, and we kind of cast that into our session types. All right. So we already know, or we have the idea that we want to treat the channels as a resource. What the heck does that really mean, right? It's very abstract. Yeah, it kind of makes sense, but I really still don't know what it means. So, just let us remind ourselves before we go in the break. What are the two structural rules that weakening rejects? Sorry, linear law. I've given it away already, one of it. So that linear logic rejects, right? We know that to reason about our inference rules, basically we have structural rules, so the structural rules of entailment, and so-called substructural logics, and linear logic is one substructural logic, they reject certain structural rules. So which are the two rules that linear logic rejects? Weakening. Yeah, weakening, right? And the other one? Contraction, exactly. So, well, okay, it's 5 past, and I'm going to resume with that next time. In particular, I want you to get the feeling for what does it mean if we don't have weakening or contraction with regard to message passing concurrency. What are the shapes? So maybe you want to think about this, okay? That's kind of the only homework I gave. Think in terms of those processes that we create at runtime. So we have the networks of processes. So we have process graphs, right? That's what we have right now. We have graphs of processes. Think about it. If we don't have weakening and contraction, what kind of structures do we get? Okay, that's my only homework, and we're going to resume tomorrow. All right, thank you.